Hello and welcome back to the AI-DC debate. This is part 2 of our GTC round-off. And in part 1, we talked about our impressions of the keynote. So obviously, only I was able to walk the expo floor yesterday, but I think that there are quite a lot of debates that are happening in the social media space. There's quite a few things that we wanted to talk about. And I was also hoping that I can just, share some of the things that I've seen, and then we can talk about what do you think? Are they impressive? So let's kick off the debate. One of the criticisms that I think NVIDIA received, not just from people who saw the keynote, but from people who went on the expo floor, is that there is nothing new. In fact, there is a few memes that have been made of Jensen on stage and then like these red letters, nothing new to say. And I can see how someone can reach that conclusion if they haven't studied what is shown in detail. So one of the things that I did is actually spend quite a lot of time on the MGX stand, and the MGX stand on the expo floor. What they were showing is every single component of the ecosystem of racks that NVIDIA has designed. And on their booth, what was very interesting is they showed each of the components of that ecosystem in terms of the compute nodes, the switch nodes, the storage nodes, but also there was like a mini data center. And in the mini data center, we saw each of the racks that Jensen showed on picture on stage. So let's talk about this announcement and this change in strategy. I feel like before, we were very focused on this singular development. Let's make a rack where we can do scale-up networked GPUs. Now, NVIDIA's really have an ecosystem of different infrastructure. You have storage, you have CPU racks, you have networking racks, you have the Grok racks, and the NVL rack with Vera Rubin, the Opteron rack. So it really has changed. To me, it feels like that is one of the big differences that have happened since last year. Manoj, what's your take on it?
Yeah, I think I won't agree with the fact that there was nothing new out there. I think there are a lot of things which I found as new, especially about the Grok system architecture, how they are integrating Grok with the rest of the NVIDIA platform. That is quite interesting to me. And also, if you look at it, it was all about NVL72 rack scale system architecture, whether it is like Blackwell Ultra, and then Rubin Ultra, the Kyber rack and all that, right? So now if you look at it, they have expanded the MGX rack with 4 other SKUs as well. I don't know whether it is called SKUs or like 4 different kind of
designs,
racks,
I guess. Rack scale designs, let's say that.
Yeah, one is the Grok 3 LPX based rack. Then there is a Vera CPU based rack. I am so surprised why NVIDIA is actually coming up with a CPU rack. And if you look at the rack, it's like 8 CPUs in a node, and that is going into a highly CPU dense rack system. That is very interesting, very new. And the other one is the Bluefield 4 STX storage. Obviously, that is something that we had expected because the Bluefield 4 storage-based system announcement came in CES. But I think this is the first time they're showing the rack scale deployment of the Bluefield 4 based storage. And obviously the Spectrum X.
So many switches.
Spectrum 6.
There was like a whole table of switches.
Exactly. So that's a line. And it's quite interesting how heterogeneous these systems are and how NVIDIA is planning to integrate these systems. It's actually, I'm sure that it's a software nightmare to orchestrate these workload across multiple configurations, whether it's like a CPU intensive activity going into a Vera CPU kind of like rack, and then some part of the inference going into Grok 3 based system. Some of it is being done in the NVL72 type systems. These systems have different kind of networking.
Let me bet in just for a second. That's basically what Jensen highlighted is that really is why he was talking about Dynamo last year. He said you almost missed it. The unique thing here that we made that you missed is Dynamo, because Dynamo enables us to schedule the workload across all of this heterogeneous infrastructure. And I do agree that many people missed it. No one talked about it. I didn't see it in the media.
No, last year even I had actually I think a LinkedIn post about Dynamo. Because Dynamo, the objective of Dynamo, at least highlighted last year, was as a software platform to optimize the GPU utilization. That was actually the purpose of Dynamo, right? So NVIDIA is actually pushing it beyond, like obviously you optimize the workloads across GPUs, and also it can scale beyond GPUs to CPU racks and also heterogeneous accelerator racks like Grok. It's quite interesting, and like having those capabilities is actually music to a lot of these ASIC vendors as well, because if they can actually integrate with Grok 3, there could be a way to integrate with other ASICs as well, right? So I'm sure that a lot of ASIC vendors who's entering or planning to enter this inference market, this is actually a pretty good thing for them, that NVIDIA itself is integrating a heterogeneous architecture into their data center blueprint, and it is possible for others to do similar things as well. So yeah, I think that's the biggest takeaway that I have from this.
So let me just give you a few kind of tidbits from my conversation with the people on the floor. So the Grok rack was made in 90 days, according to the guy that was standing next to it and kind of telling us the details about it. In fact, to be able to do it in just 90 days, NVIDIA basically found the simplest way to do it. What is the simplest way to do it is utilize as much as it was possible from the existing Grok development. And they actually focused, from what I concluded, more on the software stack to be able to integrate the Grok chips and the Dynamo ecosystem. So the rack for the Grok is not using NVLink. It uses C2C for scale-up network, and it actually does not use the Vera CPU either. It uses an x86 CPU from Intel. I thought that was very interesting. It's a very pragmatic way to think about it. It's not an ego way. Oh, we have to use our CPU. We have to use NVLink. No, it's we need to get this out. Let's integrate it into our software ecosystem, and we'll just find what is the shortest route to market so that we can get this done in 90 days.
Yeah, obviously, we were not really expecting a big architectural change to the Grok platform, but obviously, NVIDIA has made it so NVIDIA stylish, I would say.
And simple, yeah.
I would say, yeah, I don't think that like any changes they would have. I was not expecting for them to do any changes on the architecture layer, at least. Obviously, on the mechanical design, they would have done some changes. But maybe in the next upcoming generation, I think the Grok 40, LPX 40, right? Sorry, LP 35.
45.
LP 30 is,
yeah.
LP 30 is the current generation. LP 35 is the other one. And LP 40 is with Feynman.
I think they call them the LP30s and 40s, so they're trying to kind of do like generational thing, like the step functions, and then within each there is a 30 and a 35.
Yeah, LP30 ships with Rubin, and LP35 ships with Rubin Ultra.
So before I pass it on to Shane, and I think as a little segue for his impressions, for me, if one takeaway was there's an ecosystem of rack scale designs, the second one was these designs have got so neat. Like, it is incredible. And from what I heard from the ODMs that I spoke to on the floor, and also from my different one-on-ones with NVIDIA designers, there was this focus on how do we make the design very simple to manufacture, very simple to assemble, and very simple to install and maintain. The whole ethos was we want to accelerate. How do we accelerate things from months to days, from weeks to days? If we can assemble quicker, if we can manufacture quicker, if we can install quicker, if we can maintain quicker, then actually the whole ecosystem will move faster around us. So I think the Vera Rubin design is just so much better than what we saw with the Blackwell design. It's a different server. It's a different rack. It might look similar to the outside for people, but inside, even how the Vera Rubin sleds that are liquid cooled slide into this internal manifold. I've never seen anything like it. It's pretty incredible. So Shane, what's your impression? Is this one of your takeaways like me, or maybe you disagree? I'm curious. What's your take?
I totally agree. I actually think if Steve Jobs is still alive, he probably will like this new design. It's so neat, so well designed. The color is perfect. And also everything just clicks.
Did you say the color is perfect?
Yes, but it's. I think
It is.
let's be honest. This
Let's be
gold
honest.
color
It
looks
is.
very, very.
It's
very
it's pretty sexy.
Yeah, especially for high value IT equipment. And also, it's like Lego. And especially from the coolant power perspective, you look at the Blackwell design in the server, in the compute tray, there's one big piece of cold plate, but this time we have a cold plate holder, what's called internal manifold. So this shelf actually is covering the entire server, and you just click the copper cold plates into those spaces, then that will perfectly cover the chips. So that is very, very neat design. Actually, it helps a lot with the maintenance efforts. So people are worried about how should I maintain such a complicated and valuable device, and they're scared to make any movements. But nowadays it's super easy. And also, I have seen this. I've heard about this not long time in the past couple of months. Because when I talk to vendors, they would give me some hints like, "Oh, we're gonna do this one in the variable bin rack." But actually, this is the first time that we see them in real life. Many of those are for the first time. It is very exciting to see something that you have been talking about for a long time and suddenly come into the reality. So, if you remember a long time ago, we had a prediction about native liquid cooling servers. I think this is the perfect example of native liquid cooling server. SSDs are in a dedicated liquid cooled a drawer, and that is pretty special in my view. And because that means not only the chips but also the SSDs are getting a lot hotter than before, like from 10 watts to 100 kilowatts. And imagine 96 of them in the drawer would be nearly as high as a cutting edge server from last generation. So that is very, very cool, very, very neat. And also, I think there's a lot of small innovation in the entire liquid cooling system, even though that we don't discover it, but they are existing. For example, I imagine a lot of people haven't noticed that the soft pipes in the server are more or less being changed to metal pipes, and for the pressure, for the durability, and for reliability. So that is a very cool design, and actually it looks more clean because you can bend the tube to be the way you like. And also, it has improved the tin material. So it's also for the first time they are officially recommended to use liquid metal as tin material. And sort of all, they have like diamonds on the heatsink just for the thermal conductivity. And furthermore, they have also the microchannel cold plates, which has like less than or equal to 100 micros between two things in the channel. So that is all very small engineering level innovation, but that is very cool. It solves a little problem at a certain stage, and if you combine them all together, that would improve the performance of cold plate to a very, very large extent.
Just one note. So on the liquid cooling of the storage components, so the Bluefield 4 STX, the storage rack, I saw two versions of the actual device. One was made by Supermicro and it was air cooled. To be honest, now when I look at an air cooled server, it looks a mess. Next to it, there was a QCT storage STX version that was liquid cooled with both the Bluefield module, the DPU being liquid cooled, and also the SSDs being liquid cooled. And that was the first time that I had seen SSDs being liquid cooled. It's actually a very small array of SSDs. It's not very large. In the Bluefield 4 design, the focus is not on huge capacity. It's actually on performance. But it was very interesting to see a manifold going into somewhere. Unfortunately, I'm guessing QCT did not want to show everything. So there was actually everywhere on the NVIDIA booth, some things were hidden with these black covers. And so I couldn't take more photos of the Bluefield racks to see more of how the liquid cooling of the SSDs was working. So it's a little bit of a secret in terms of the organization of the rack. QCT were not showing it, but it looks very neat. Inside, it's like incredible. It's my dad, who loves cable management's dream to look at this rack. So one other thing that I thought was very interesting, Ashen, is obviously we've talked a lot about high capacity CDUs. We've talked a lot about 800 VDC. Last year, when I look at the MGX stand, the ecosystem of components that NVIDIA was inspired by the OCP and adapted to their design, everything was, manifolds, busways. This year, on the other side of what was exactly the same display as last year, there was a whole new row. And in that row, you had power side cars. It was breathtaking just how many power side cars you saw. And then next to it, there was so many components that were power related for step down function of voltage. And then there were so many CDUs that were huge, the biggest CDUs I've seen. I mean, to be fair, I have seen a 2 megawatt CDU before, so I knew that they get bigger, but we've never seen a display where you end up seeing many companies as products, one next to the other. I mean, NVIDIA is really the only person who's doing it. So it was quite breathtaking and it was quite surprising. So just on the topic of the power sidecar, what I found very interesting is just that there was sidecar from Vertiv, from Schneider, from Megmeet, from Lighton, from Leadwealth, from Flex, from Delta, from maybe I'm missing something. It's easy to miss something. It was crazy. I've never seen anything like it. So how do you interpret all of this? Does it feel to you that there is a maturation happening in the 800 VDC and the high power capacity CDU ecosystem? And what should people think about that? What does that mean in practice?
Yeah, so let's start from CDU side. I think it's so we know already the big CDUs are coming up. We have already seen a lot of those. But the new thing is that the big CDUs are now compatible or powered with 800 VDC directly. That is quite special. So in the past, before when we first talk about 800 VDC, we're saying that the ITs are going to powered by 800 VDC, but since you have so easy access to the AC, all your facilities will be still powered by AC power. But nowadays you can think about it, because of the IT power are so large, and therefore you need a super large capacity CDU. For a 2 megawatt CDU, the power consumption of that would be very, very high. You can just divide by 20, 2 megawatts divided by 20, that would be 100 kilowatts. So this is a quite high power, and therefore they're also using 800 VDC to power it. But this actually is making things more complicated, and that's why the CDUs are so big, because normally the pumps, the motors are powered by AC, so they need the frequency to drive the speed. But nowadays, if you have DC inputs, then you have to revert it back to AC and make some frequency adjustments to control the capacity or the output of the motors. So I think that means the gray space, the CDU in the gray space will merge to some extent with the ITs in the white space. So CDUs probably will not be far away from the IT room, but they will be at the end of the row or next to each other, next to each rack. So
that works really well if you have two-phase CDU, because the two-phase CDU, you kind of don't want it to be too far from the racks. So it would work very well in a two-phase setup, actually, because for one phase, you could have put it anywhere you want.
That's right. For two-phase CDU, that is definitely the case. And two-phase CDU actually will have a very good opportunity because the density becomes so high. And to be honest, compared to immersion for single-phase direct-to-chip, two-phase direct-to-chip has a very big advantage in terms of cooling capacity per chip, per square centimeter. And then on the power side, I think the sidecar, that's the MGX ecosystem that Manoj and I have seen that at the OCP event last October. And we also what shocked us is, if you look at if you go to a OCP event in the past years, you probably will see all the ORV3 stuff, and they look more or less the same. But nowadays, because they put every stuff in the sidecar, you don't have to stuck your stuff in the IT rack, so you have the freedom to design them. And every company have different designs. They mix the way they mix CDUs and BBUs and power shelves, the way they arrange the power shelves in the rack. You can put two in a row or three in a row to achieve 110 or 60 or 55 or 33. So they have the freedom to do that. And I think for vendors, for end users, that's also a good thing, because you can freely choose from all different kind of vendors. They would offer you different specialties, and you can also have the freedom to adjust the ratio between BBUs and CBUs just according to your demands. And because the sidecar is a separate rack, so it does not impact your IT, as long as you can see that as a black box, right? It gets gets inputs and provides some level of output. What happens in that black box, we don't have to know. Just make the arrangements according to your own demands. And also, I think you have seen a lot of secondary power boards as well, from 800 to 50 to 12 to 6. I think that is also a very thriving market, because this kind of a secondary boards will be soon used in servers. If not in servers, this kind of design can also be implemented in PowerShells.
It's so interesting because if I go back 10 years to when I did my very first project of assessing the OCP ecosystem for the OCP, some of the interviews that I was doing at the time, people were so much complaining about choice and about compatibility. I want to be able to buy components from different places and have choice. And at that point, the OCP ecosystem was already a few years in. The MGX ecosystem is new. So to have this level of choice and this level of compatibility is pretty unprecedented. I have personally not seen something like that because you can choose any of these power sidecars and it would work with any of the other components. This to me is very unique.
Yep.
I think it is just about like creating the ecosystem, right? So the point is like to deploy this kind of volumes, you need to build that ecosystem. It's not really like once you work with one of the vendor, he will be able to fulfill all the demand, right? That is not the situation right now. Especially when we are talking about like 6+ million GPU shipments in a year. Those are like highly complex GPUs which requires specialized cooling and has got like very sensitive connectivity. All of those things has to come together. NVIDIA is just like putting out the specification. Obviously, they're designing it, or they're working with partners to design it and making sure that designs are out there for its partners to take out and replicate so that they can build enough volumes. And if you look at it, that is what exactly OCP used to build, like reference designs and architectures so that companies can take it and build it. And obviously there is a demand from the hyperscalers. So that was the whole thesis for OCP. But what happened with OCP is that like the companies who was promoting OCP started building their own custom stuff. For example, Microsoft building a Cobalt 100 or Cobalt 200 CPU. So if you are actually releasing a reference architecture based on that design, nobody's going to get it, right? Because the CPU is exclusive to you.
Yeah,
so what is actually the
Meta
point of releasing it to... Yeah, so what's actually the point of releasing into OCP? So that's why I think OCP right now focusing on like specifying standards. Basically, I would call OCP as a standards body right now on how to build systems which is actually deployable at scale and also optimizes all of the resources. We're like looking at from the thermal standpoint, power standpoint, interconnect standards, all of those things, right? So I think some of the traditional standards organizations, whether you're looking at IEEE or many others, they're very slow to respond. So the hyperscalers have their own like consortium now, OCP, and they can specify either the NIC form factor or the accelerator form factor or the rack architecture. So I think that's how OCP is evolving. But NVIDIA has to do it because to fulfill the volumes they are driving now, there is no other way to do it.
So a few little tidbits. So I obviously told you that I spent a lot of time at the NVIDIA booth, no surprise. Apart from all of the Kyber racks and all of the new storage racks and the Vera Rubin racks and et cetera, they also had a bunch of robots. They had a lot of things. So it takes you a long time to actually go through it all. I spent just 30 minutes on networking and 30 minutes on storage and 30 minutes to compute. It takes some time. But I ended up spending a lot of time at the MGX ecosystem because there was one very chatty engineer from one of the vendors who I wanted a simple question answered and he wouldn't answer it and I wouldn't give up. So we ended up being there for almost 2 hours. And my simple answer is, why are these power sidecars designed different? What do you think is the merit of each? I wanted his opinion. He just refused to give me his opinion and I kept asking. And then, 2 hours later, we had gone around the MGX booth several times and we had gone round and round in circles until I kind of got it. My takeaway is this: they will all sell out. Actually, the demand is so high that all of the capacity of sidecar that is out there is all going to sell out, which I thought was so interesting. I really needed to hear him say it. So I thought that was very interesting. And then the second thing that we spent quite a lot of time talking about is I already had an inkling from some of my previous discussions, but I wanted to get more confirmations. So the new design of the Vera Rubin rack, the new Opteron optimized design, is actually going to continue to ship up until 2030. and then the Kyber rack will also ship. So the Opteron and the Kyber will continue to run simultaneously. That does have implications on power because the Opteron rack is less dense than the Kyber rack. So what the power sidecar designers now expect is that for the Opteron rack, it will also run on 800 VDC.
Operon rack. Okay.
Operon. Sorry, I keep saying Opteron. Sorry. So the Operon rack will also run on 800 VDC, and there will be one sidecar that's connected to several racks. And because it's less dense than Kyber, and then for Kyber, it's probably going to be then 1-to-1. So I thought that was very interesting because when we thought about 800 VDC, for me, Kyber was one of the really big drivers, but there is a change now, and the Operon rack, how it's been redesigned, it's so clever and it's so easy to install and build. It makes sense to keep it for a long time. And clearly that is now the intent. And I think it will probably have pretty good demand throughout the forecast horizon, but it will be a part of the 800 VDC ecosystem.
Yeah, I think when we are talking about like sidecar, there are various use cases right now, right? Earlier, we were only talking about like one Kyber rack, one NVL72 rack. Now we have like 5 different rack configurations. And also these rack configurations cannot be exactly the same. It could actually be different. For example, the NVL72 configuration, AWS and Meta deploys in a 2-rack configuration, not really in a single rack configuration. So there could be like various changes. For example, the Vera CPU rack, they have, I think, 32 nodes of Vera CPU in one rack. It is possible that like customer deployments will actually change. Some might actually club the Vera CPU rack with maybe a Bluefield switch rack, half and half, to create a different combination of it because the unified communication language is Spectrum X Ethernet. And also the data center configuration, whether you have a battery energy storage systems, which is outside, whether you are having a direct power feed, all of those depends on what exactly is the sidecar requirement that you have. Some of the sidecars will have like lesser battery backup. Some of them may not have a battery backup. It will be completely a capacitor banks and then maybe BESS for redundancy, right? So there are a lot of like combinations possible. So I'm not surprised that like there are like various PowerShelf configurations out there. And I think for the PowerShelf, there are a lot of suppliers, especially for the power semiconductors. And these guys have different architectures. So whom you are aligning with also matters on your PowerShelf design and PowerShelf density design. So all of those things will actually influence the design of the PowerShelf rack. So I'm not surprised that it is like various configurations you are finding it out there. I think the output profile.
I think for me, it was the pace that was surprising, not necessarily just the configuration. It was the pace. And I just wanted to almost, kind of create a bit of controversy. I just wanted him to tell me, I think this is better, or that is better. Ultimately, each of the vendors can also support different options, right? Because it's modular. So Delta can decide to put more or less CPUs.
Yeah. The thing is, so for PowerShelf, there's one problem that the power electronics are in short demand. And if you want to make PowerShelf, you have to look for suppliers and you have to make compromises to optimize your output, optimize your design. So if they want to make a very slim and compact PowerShelf with super high power density, then they're going to buy the most expensive power components, which is probably not available. Then different vendors will compromise to a certain extent. For example, they choose less dense switches and they put more of them to increase the power, so the space would increase, the size would increase a little bit. As long as they deliver the same amount of power, nobody cares how they designed. And for people who don't have the design capability, a company like Infineon, they provide reference design if you buy their whole kit, but the reference design is not perfect. So everybody still need to make some adjustments. Then they would like provide different solutions because there's no standard. People nowadays would like to see that as a black box. As long as it delivers, nobody matters.
I really liked one of Jensen's response on the 800 VDC topic. And it was, the question basically that he got asked was something like, why do you think that it will happen? It's very challenging. And he said, I don't know. People told me that liquid cooling is very challenging at the scale that I told them I want to do it. And we did it in a year. So all I'm going to say about 800 VDC is watch me. I really like that confidence. And they're actually going to build a data center that is 800 VDC as a demonstration to the industry, which I thought was also cool. And then one very fun thing that I saw on the expo floor when I was talking to different ODMs. Some of them might make one example of component, another one might be IT, one might be OT, ODM. They had met and had a chat about what they want to do for Computex. And they're going to make a joint multi-ODM 800 VDC booth because they think that then Jensen will come to their booth at Computex. And then that's going to create a lot of pull. And I thought, this is just amazing seeing that level of creativity. On the last topic, so there was one new device that I thought was very interesting. That was probably the moment when I realized that NVIDIA's storage roadmap and what we're going to see in devices are much broader than just a singular STX4 rack that we saw being launched. I think that we're going to see quite a few different devices. And the reality is, when we met with the DGX leader of the group, he said that they just see the need to do that storage in practical deployments has created a bottleneck. He told this one story of how they had in the first generation of DGX a client who bought several DGXs, and then they were very happy with it, so they bought several more, and their performance didn't improve. And it turned out that how they had connected the storage to the compute was the problem. The storage was in one building, the compute was in another. There was very low bandwidth connection between the two. That's when they started to realize the storage design, the storage connectivity, everything, in terms of that ends up being one of the biggest bottlenecks. So then we have to start working on storage. So then there was one interesting device. It was a GPU initiated storage server. So Wiwin showed it at their booth. It had space for 96 SSDs, and actually all of the SSDs were liquid cooled. And it was like a slightly modular style design where on the top are the SSDs, and in the drawer underneath there are PCIe cards with the RTX version of the NVIDIA GPU generations. Right now they showed it with Blackwell, but next it will probably be the Rubin RTX, and several takeaways. So the SSDs where they see the power capacity of the SSDs getting to is about 100 watts. Once the SSD performance is improved to match what NVIDIA want to see. About 10 years ago, the SSD power capacity was 10 watts. So it's already grown to 40 to 60, and they now see it going to 100. That's why they already wanted to be ready, and they designed this entire liquid cooled chassis. So the cold plate that the SSDs slot into, it looks like a drawer, actually. And the 96 cold plates all slide into the cold plate, and they're cooled on each side, and every single SSD is cooled on each side and between each SSD. That's a whole new market for liquid cooling that we haven't seen before. And I think it's very interesting from a physical design perspective, but it's also very interesting in terms of a storage market disruption perspective. What do you think about it, guys? Because I think this is pretty different from what we've seen from this storage ecosystem before.
Yeah, I'm quite surprised that the way or the configuration of how the storage is connected to the GPU nodes are actually a bottleneck. The biggest challenge for storage, I think which is widely accepted in the industry, is actually coming out of the KV cache management, right? How's the KV cache is evicted from the GPU, HBM, and also the DDR memory of the server, so that other user profile and also the context can be loaded to the GPU and do further interaction with the LLM using that newly updated KV cache. And also every interaction that we have with an LLM, right, create a ton of KV cache. And this actually provides the context for LLM to respond to us. So evicting KV cache and storing it somewhere basically saves all those compute cycles that you have already computed. And storing this KV cache becomes very important so that you can save a lot of energy, compute cycles, etc. How to store this KV cache, how to retrieve it fast, and then make the system ready for new user prompts has become one of the burning problems in storage. And that is exactly why we have seen crazy demand for storage, like people running out of SSDs, flash storage, and even tape drives are out of stock, primarily because of this crazy demand coming up. And when you are talking about image and video further, it actually increases the KV cache demand much more. And also for training data based on video and image, that also is like quite a lot of like storage intensive. So I guess NVIDIA's approach is like, I had an interaction with Kevin before, Kevin Deerling, who's actually the guy from NVIDIA's networking.
He's like one of the most important networking people in the world. But Manoj is just friends with everyone. So he's like, Elon this, and, Zook this, we're just casual friends, it's fine.
No, Kevin and Gilad are pretty good friends. And I guess, I don't know whether they will say this, but I say that. Interestingly. Anyway, so he pointed out one thing very interesting. So traditionally, the enterprise storage is designed to save every bit of data, and they create redundancies. They create like making sure that every data points or every bit is stored and retrieved correctly. This actually creates a lot of overhead on the storage architecture, storage platform. And that is important for enterprise storage because our personal data, our credit card information, our financial transactions, nobody wants to miss a bit of it, right? So every data point is so critical and we need to have that stored correctly. So it's very important. But evicted KV cache is not that important because if there is a like corrupted bits here and there, it does not really matter for LLM. And also, in case if it is completely gone, you can recompute it. We are actually storing this data to save compute cycles. So that means that you can have a fast storage architecture, which is not really focused on like data redundancy or like data I would not say security, but so that actually gives multiple vectors for engineers to design faster storage. And that is what like the need of the hour for NVIDIA. That kind of storage does not really exist and they have to create it. That is what they're trying to do with NVIDIA Bluefield 4. And maybe that is actually the reason why they have to even like create a cold plate for the SSDs because SSD is going to have a tough time. The read writes are going to increase dramatically because of this. So yeah,
Manoj,
that is a possibility. And maybe you need to have some kind of specialized like SSD which can withstand this high read write demands.
Manoj, how do you interpret the GPU initialization, the fact that they are GPU initiated, not CPU initiated?
Yeah, basically, when you have an orchestrator, the orchestrator can actually like orchestrate the KV cache eviction directly from the GPU to the storage node. So it's like the Rocky networking, right? Like RDMA over Ethernet. So you bypass the CPU completely, and the data comes to like the storage box correctly.
Yeah, it's a bypass mechanism. That's exactly how I interpreted it as well. So, Shen, it sounds like there is basically a net new opportunity for you in the liquid cooling space. We need to develop a second model now that doesn't look just at chips. It also looks at SSD.
I think we just need to be more future-proof, not only SSD, but also for power supplies. Maybe in the future, in the short future, there'll be liquid-cooled power supplies, liquid-cooled power shelves, liquid-cooled BBUs. I've already seen immersed BBU plans for an immersed bed system for data centers, and also the liquid-cooled everything in the server. Yeah, so we need to be more future-proof about that. A lot more easier.
We've already taken a lot of our listeners' time. This was supposed to be a quick, roundup, but there's just so many things to cover. The innovation here is so incredible that I feel like it was important to at least focus on a few devices and to really talk about their merits. We've already decided what's the topics for next time. It's our roundup of the OFC. So we will see you very soon when we give you our impression on what's the latest innovation in networking. And thank you for joining us. We'll see you very soon.